Hi everyone. Today we're going to be learning about electrical circuits. This is a rather important thing to know, and you'll be doing many experiments using electrical circuits in your school lab. Now, an electrical circuit is simply a circuit of conducting material, that is a circle or conducting loop, that electricity flows through. Of course, the wires making up this loop might end up being tangled or whatever. The point is, they form a complete circuit going all the way around. All electrical circuits contain a power supply. Now, the power supply might be a battery or a box, which will produce a potential difference, or a voltage. The voltage is able to pump the electrons through the current. Sometimes this voltage is called an electromotive force for this reason. So we have the power supply, and it pumps the charge carriers through the circuit, producing an electrical current. The power supply can either produce a direct current, that is DC, or an alternating current, that is AC. If we have a battery, it'll produce direct current. If we have the power mains, it'll produce an AC current. So a DC power source, like a battery, only pushes the electricity in one direction. The chemical reaction inside a battery causes a constant fixed voltage to appear at the ends of the battery. So this will simply constantly push electrons in one direction. Now, an alternating current, as you might have guessed, is a little different to a direct current. An AC power source will alternatingly push the electrons forward and then pull them back, then push forward, then pull back. So this means that instead of just a constant electric field being pushed across the circuit, we get a changing one that goes back and forth and back and forth. The rate at which it varies back and forth depends on what we call the frequency of the alternating current, how many times the power source switches per second. Now, we use AC power a lot, especially in our homes, because it's easier to transmit through power lines than DC current. Of course, for small experiments in the lab, you might use DC current because we don't have to transmit this long distances. The Australian power mains contains an AC current that switches back and forth 50 times every second. So 50 times in every second, it pushes the electrons forward and then pulls them back. This means that we say that it has a frequency of 50 hertz. 1 hertz is the same as 1 per second. So 50 hertz means 50 per second. The average magnitude of the voltage is 240 volts. So if we were to take the average distance of the voltage from 0, we'd end up with 240 volts. Of course, if we were to take the average value altogether, then the amount of times the electrons are pushed forward will be balanced by the amount of times the electrons are pushed back. And so the true average voltage is 0. This, of course, is not very useful, which is why we use the average distance away from 0, whether that's positive or negative. Now, many electric devices require a DC power source rather than an AC power source, which is what's provided by the Australian mains. And so we use something like this to change the AC power into DC. If they are plugged into the mains, they will need to contain a diode, which is what this is a photograph of. So what does a diode do? The diode acts like a valve. It will allow electrons to pass through in one direction, but it won't allow them to pass back in the other direction. So the diode acts like a valve and only lets electricity flow in one direction. If we have an AC power source moving forward and back and forward and back, then the current that can pass through the diode will simply go forward and then stop, and then forward and then stop. It can't go back through the diode. Most electric circuits contain at least one device or load that will use up the electrical energy. Remember that circuit components, as we learned about when we talked about the energy of electrons, will use up the energy of the electrons. And so these devices are what we call the load of the circuit. They're the things that do useful stuff. Electricity can be transformed into heat energy, mechanical energy, sound energy, and so on and so forth. We can get many, many different forms of energy out of electricity. A circuit without a load that is, without a device that transmits electrical energy into one of these energies, will damage the power supply. The reason for this is because if there's no difference and no way for the electrons to lose potential energy, then they'll just gain enormous amounts of energy passing through the circuit. And when they reach the battery again, this can cause the battery damage as it heats up. Now, when drawing a circuit diagram, we tend to follow specific conventions. It's important to learn how to draw a circuit diagram because you'll probably need to for some of your laboratory work. Wires are always drawn as straight lines, and they always meet at right angles. We can see that in this extract from a much more complicated and quite facetious circuit diagram. Circuit elements are sometimes represented by circles with symbols inside, sometimes letters. So let's take a look at what a real circuit diagram looks like, as opposed to this joke one. We have here a pair of typical circuit diagrams. I've drawn a number of circuit components on each one. So this little jagged line here is what we call a resistor, or how we represent a resistor. Sometimes, instead of drawing it like that, we might represent a resistor like this, simply with a rectangular box. And perhaps, just to make sure it's not ambiguous, we can write an R on the front for resistor. At the top of this diagram, we have a switch. That is, something that we can open and close in order to allow current to flow through the circuit or stop it from flowing through the circuit. On the bottom, we have an ammeter, which is a circle with an A inside of ammeter. On the left, we have a voltmeter, a circle with a V inside for voltmeter. Pretty straightforward. Finally, we have a DC power source. Now, when we draw a DC power source, one end of the power source will always be positive, and one end will always be negative. It won't change, because it's a direct current. So the positive end we draw as a long line, and the negative end we draw with a short line. Let's go on to the other circuit that we have over here. We have an AC power source, which is a circle with a little sine wave symbol inside it, right? Looks something like this. So this is a representation of what the current does. If we were to draw a graph of the alternating current, it might look something like this, going back and then forth. So we use this symbol to represent a power source that goes back and forth and back and forth. We have here a globe. Sometimes these are just represented by a resistor because globes are simply resistors that glow brightly. So we can see that there's a sort of circle representing the glass bulb and a little turn inside representing the filament. The variable resistor looks much like a resistor, except we have a little arrow on it. So we can move the arrow left and right to change the resistance of the resistor. Finally, we have Earth. Now, what could this mean? The Earth means that we have this wire plugged into something that is always completely neutral. And no matter how much current flows into it, it will remain neutral. If we look at the ground, or the Earth beneath our feet, the planet is so large that any large amount of electric charge flowing into it will not change its charge very much. So we can always treat the Earth as neutral. And this means that current can flow in interesting ways through this circuit. Now remember, in circuit diagrams, current flows from the positive terminal to the negative terminal. This is the direction of the conventional current and the direction that the electric potential drops. So if we have a positive end of the power terminal over here, then the current will flow away from the positive and towards the negative. The electrons move in the opposite direction because electrons are negatively charged. Don't be confused by the arrows in a circuit diagram. The arrows in the circuit diagram show the direction of the conventional charge, or the conventional current, which is positive. In reality, the current is caused by negative charges. So, this is the end of the theory. We've learned about circuits and how to draw circuit diagrams. Let's go on to some questions.